So now we will use PyTorch and do a complete implementation to have this IIR filter implemented as a recurrent neural network. So we import here PyTorch. We will define some parameters. So the in features equals to 1 is the samples per input time step. Hidden size is the number of hidden states, so the memory elements we are going to use, and we're setting it to 3 as we discussed previously. Outputs is equals to 1, so this is samples per output time step. Then we decide the number of layers, so we'll use 1 layer, and we will set batch equals to 1. We also been using many times this functions. There are many ways how we can do this. We've been using the signal to PyTorch, which converts our audio signal to the PyTorch format for the recurrent neural network. Then we compute the coefficients for our IIR filter, like we did before. And this is exactly what we did before. So we see it also sounds the same. There's no news here. But we will use these coefficients as weights. So we will replace, for example, values in our weight matrices by these coefficients that we calculated in a way that our recurrent neural network will work as an IIR filter. And here we see, for example, that we have the recurrent neural network as IIR filter. So the hidden states age as delay chain, waits for updating, age for shifting the delay line, and this is what we also saw previously. So for example, if A1 is equals to 2 and A2 is equals to 3, then our array will become, there is this array here, 1, 2, 3, 0, 1, 0, and 0, 0, 1. We can first apply a shift operator S, and then the coefficients H multiplied from the right. So we are doing a dot A times dot product of A and S. We have our S array given here, we have our A array here. This will be the resulting matrix, and this is the W H of H. So we will have here 2, 3, 0, 1, 0, 0, 1, 0, 0. Looks very similar to this here. A1, A2, 0, 1, 0, 0, 0, 1, 0. Now we can create our neural network model and assign our desired weights such that it acts like our IIR filter. So pay attention here that we are not training this moment, so we are just using the architecture of a recurrent neural network to behave like an infinite impulse response filter. So we will, when we create our network model, we will assign our desired weights. And this is what we are doing here. And we have here our K1, our K2. So we are taking this weights, and then we are assigning the weights that we want to the proper position in the weight matrix. So with the Spring function, you should check at runtime if the weights of the model now look like what we expect. And if they look okay, we have now a functional neural network which should work similar to an IIR filter. And we can then, for example, convert our impulse to PyTorch and then feed it to our neural network. What we're doing here, have our impulse here, our impulse, then we're converting to PyTorch, and then we are feeding our neural network model with this signal, and this will will give us the output signal. And the output of the recurrent neural network is then converted back to NumPy, so we can play it back to the speaker for listening comparison, and we can also plot together with the output of the IIR filter for visual inspection and visual comparison. So this is what we're doing here. So remember that now this is the output of our recurrent neural network, and it sounds like this. And it sounds exactly the same as from the IIR filter. And here we can also see visually, so this in blue we have the IIR filter impulse response. It would be, let's call it our target, and the output of the recurrent neural network. And we see there is the same shape, apart from that the output from the RNN is somewhat smaller, and this is because of the 10H function. And this shows that a recurrent neural network can be indeed set up to function like an IIR filter. And this creates an interesting connection between recurrent neural networks and infinite impulse response filters, and hence RNNs can be viewed as a generalization of IIR filters.